Welcome to Tomorrow Unveiled. The last few years felt like AI was learning to speak, learning to generate text, to chat, to summarize. In this first week of December 2025. This feels different. This is the week it stopped just participating and I think decisively started thinking. We're seeing a really foundational shift here, a permanent move beyond what we call the chatbot era and deep into the reasoning era.
It really is a shift. This wasn't just another incremental update, not at all.
Exactly. Our sources are showing a complete barrage of breakthroughs that have, fundamentally altered three critical things: the sheer capability of these systems, the cost to actually get that capability, and maybe most importantly, the massive widening safety gap this is all creating.
That safety gap is becoming a huge story.
It is. So our mission for this installment of Tomorrow Unveiled is to take this huge stack of corroborated findings our dedicated research team has compiled and just distill it. We want to pull out the three major interconnected narratives that really define this inflection point.
And these aren't just market headlines, right? These are seismic shifts.
Seismic is the right word. Okay, so first, we are seeing what we're calling the global reasoning war. The intelligence, the raw capability, it's converging between open and proprietary systems, but the way they're building them, the architectures, wildly diverging.
Creating this fierce competition on efficiency.
Exactly. And second, AI gets physical.
Yeah.
The magic is moving out of the cloud, out of the digital world, and into our physical world. It's not just generating code anymore, it's generating matter, it's controlling robots.
Right, embodiment.
And then third, the critical lag. The infrastructure that powers all this is scaling exponentially. But the safety, the governance, the ethical frameworks we need, they're lagging way, way behind it.
Okay, let's unpack this. The sheer density of innovation this week, it really does suggest a true inflection point. Capability seems to be outpacing even the most aggressive roadmaps. What stands out to you immediately when you look across everything our research team pulled together?
For me, it's the simultaneity. The sheer fact that all these launches happened at once. You have DeepSeq, Anthropic's new Claude, Google's latest Gemini work, all in the same week.
Right. And they were all clearly aimed at solving the same fundamental core problem: making AI reliably think over long periods. We're not just talking about predicting the next word in a sentence anymore. That's old news.
This is about something deeper.
It's about persistent agents. Agents that can, prove a complex mathematical theorem or autonomously manage a huge multi-day project at a company across hundreds of files. It's all about agentic reliability.
And the consensus from the research team's findings seems to be that the real competition now is about who can deliver that persistent reasoning most efficiently.
That's the new battlefield: efficiency.
That brings us perfectly to our first major narrative then. The global reasoning war: efficiency and persistence. For years, the big proprietary models had what some people call the compute moat.
Right, the idea that only a few huge companies could afford to play.
Exactly. Only those with billion-dollar budgets, massive data centers, and access to all the world's GPUs could get to that frontier intelligence. But the sources we have suggest that moat is now under serious threat, not from brute force, but from pure architectural innovation.
Precisely. The research data really points to this. The focus has definitively moved from just, adding more parameters, more neurons to the brain, to achieving this sophisticated agentic reliability and architectural efficiency.
So working smarter, not just bigger.
And the biggest, most disruptive data point on that front this week, confirmed across multiple analyses, is the performance of DeepSeek V3.2.
Okay, so DeepSeek V3.2 is an open source model, which, according to the documents, is matching or even exceeding the big proprietary frontier models like GPT-5 and Gemini 3.0 Pro on some key benchmarks.
It is. It's a huge deal.
For the open source community to be challenging the titans of AI on the absolute frontier of intelligence, that really changes things, right?
Yeah.
For democratization, for the cost structure of this whole industry. But how? How did they pull this off? Did they secretly get their hands on a massive new GPU cluster?
No, and that's what's so incredible. This wasn't about more hardware, it was about better math. They effectively solve a fundamental, let's call it a physics problem of large language models. The real aha moment here is something called DeepSeek Sparse Attention, or DSA.
Okay, so to really get why that's so revolutionary, we should probably quickly revisit how traditional LMs work, right? The core inefficiency.
Yeah, that's a good idea. So let's ground this. When an LM processes text, it uses what's called an attention mechanism.
Okay.
And when it's processing a document, a traditional model has to calculate how relevant every single piece of information, every token is, to every other token in the entire input. That's how it holds context.
And if your document has a length of, say, L, the computational cost of that attention grows quadratically, so L squared, or O of L squared.
Exactly.
So if you double the length of the document, the cost doesn't just double, it quadruples. And that quadratic cost problem is exactly why long context models used to be so incredibly expensive and slow to run. It basically locked out anyone but the giants.
It was the moat. And that quadratic cost problem is what DeepSeek's DSA architecture threatens to just eliminate, for many tasks anyway. DSA solves this by reducing that complexity down to a linear relationship, O of LK, where K is just a small, dynamically selected group of relevant tokens.
Okay, let's use that analogy our research team flagged, the 1,000-page book analogy. How does the old model read it, and how does DeepSeek read it?
Right, so the classic LLM, if you ask it a question about a 1,000-page book, it essentially has to physically scan every single word on every single page for every attention calculation, just in case one of those words holds the key.
It's pure brute force.
It is. It's absolute brute force calculation across the entire thing, and that's why the computation cost just explodes.
So how is DSA different?
DeepSeek's DSA is. It's like an incredibly efficient, purpose-built library indexer mixed with a smart router. It first uses this very lightweight computational step, they call it a lightning indexer, to instantly figure out which sections, which paragraphs, maybe even which specific tokens might be relevant to your question.
So it does a quick scan first.
Super fast one. And then, only then does it apply that heavy, expensive attention computation, but only to the handful of most relevant pieces of information. It's like it only reads the 2 most relevant pages in that 1,000-page book instead of scanning every word on every page.
That is genuine efficiency. You're decoupling performance from the brute force cost of compute.
Yeah.
This is what fundamentally challenges that proprietary compute moat we were talking about. You're not just building a slightly smarter model, you're changing the underlying physics of the cost structure.
And the immediate implications are just staggering. I mean, you're cutting long context processing costs by up to 50%. You're increasing the throughput, the speed it processes information by 200 to 300%. DeepSeek V3.2 basically demonstrates that really clever architectural innovation can be a substitute for massive multi-billion-dollar capital investments in hardware. This makes state-of-the-art reasoning accessible to a much broader range of people.
And the performance data really seems to back this up. The sources highlight the specialized variant, DeepSeek V3.2 specially, which achieved a gold medal performance at the 2025 International Mathematical Olympiad, the IMO.
And the International Olympiad in Informatics. These are not trivial competitions. This isn't about writing a nice poem. This is rigorous, verifiable, step-by-step reasoning.
The single most striking metric, though, that I saw in the research was from the DeepSeek Math V2 variant. Our team noted it scored 118 out of 120 on the Putnam competition.
Which is just unbelievable.
To put that in perspective for you, the Putnam competition is this notoriously difficult undergraduate math competition in the U.S. and Canada. The median score is offered 0. Like, literally 0. A score of 90 is usually enough to be the top human score in any given year.
That's right. So the fact that an AI is definitively scoring 28 points higher than the top human performance, that's not just a win, it's a categorical shift. It is absolute corroborated proof that these systems are reasoning and generating mathematical proofs at an elite, specialized human level. Arguably, they're surpassing it.
But reasoning is more than just getting the right answer, right? It's about verification. And that's where this crucial innovation of thinking and tool use comes in. The sources say this is vital for agents that need to self-correct.
Correct. The core breakthrough here is the agent's ability to maintain a continuous internal reasoning chain, even when it's calling external tools, like a code interpreter or a search API or a calculator.
Okay, so explain the difference. In the older generation of AI agents, what happened when they tried to use a tool?
In those older, more brittle systems, the internal chain of thought would often, well, it would stutter. It would break or basically reset once the agent went outside itself to use a tool. It would execute the external code, get the result back, and then it would try to graft that result back onto its internal hypothesis, but it would often lose its overall long-term strategic coherence. It was very prone to single-step errors.
So it could run a calculation successfully, but then it might forget why it ran the calculation in the first place.
That's a perfect way to put it, exactly. DeepSeq V3.2 Special, which was trained on over 85,000 of these complex instructions, can now formulate a high-level hypothesis, write the code to test one small part of it, execute that code, analyze the output or the error message, and then refine its initial hypothesis, all without breaking the continuity of its internal reasoning state.
That robust self-correction.
Yeah.
That must be what enables that rigorous proof generation we saw in the math competitions.
It is. They're teaching AI not just to solve problems, but to check and correct its own work rigorously, on the fly. It's a huge step.
So that's the open source challenge.
Mm-hmm.
Efficiency, democratization, rigorous self-verification. I mean, this has to have sent a major shockwave through the industry. What about the proprietary response? They must have been hitting the code red button when they saw these numbers.
Oh, they absolutely were. Our research team confirmed that the intensity of this competition, from DeepSeek and others, it forced a major strategic shift at OpenAI. The CEO, Sam Altman, reportedly issued an internal code red.
The code red, wow.
Yeah, and that resulted in a big reallocation of resources. They moved people away from some consumer products to focus everything on regaining that reasoning crown. And this pivot manifested in GPT-5.1 CodexMax.
So if DeepSeek's big play was speed and efficiency, where did OpenAI focus its resources? What was their architectural innovation for CodexMax?
Persistence and utility in really complex enterprise workflows. Their big innovation is a technique they call compaction.
Compaction,
Oh,
okay. So DeepSeek manages long context by being sparse and selective. OpenAI, with compaction, it sounds like they're being recursively summarized and dense.
That's the key trade-off, and it really highlights this architectural divergence we're seeing. DeepSeek prioritizes low latency, low cost per token. OpenAI is prioritizing reliability over time for these massive complex projects.
Okay.
So with compaction, instead of just dropping old tokens when the context window fills up, which is the standard memory loss problem of LLM's CodexMax, actively synthesizes and compresses previous reasoning steps and states into a dense, proprietary, latent representation.
So instead of throwing away the first 100 pages of project documentation when I get to page 101, it basically writes a 5-page summary of the key takeaways from those first 100 pages and keeps that in its working memory. It maintains the coherence.
Exactly. It's not truly infinite context in the physical sense of holding every single token, but it simulates infinite memory by maintaining this deeply persistent, high-fidelity summary of its past work. And this is absolutely vital for enterprise tasks.
I can see that.
If a developer tasks CodexMax with a huge multi-day project refactor, compaction ensures the model doesn't forget the initial architectural constraints or the user's requirements as it's churning through hundreds of files over, say, 48 hours.
This sounds like the ultimate agentic workhorse, really designed for deep technical commitment. And our sourcing confirm it's natively trained to operate inside these complex enterprise environments, right? Manipulating file systems, executing commands.
Right through the operating system interfaces. The product isn't the chatbot anymore, it's the agent that lives inside your terminal, managing vast complexity. And that native OS integration provides a really significant competitive lock-in. It's aimed squarely at high-value, long-term enterprise contracts.
Okay, so that's OpenAI. Meanwhile, Anthropic, who are known for their big focus on safety and alignment, they also delivered a major agentic breakthrough with Claude Opus 4.5. They seem to be carving out their own unique space in this war.
They absolutely are.
So what's their key competitive edge? Where does Claude win?
Anthropic's advantage is self-refinement speed and verified safety in terminal usage. There was one fascinating detail our team pulled from the internal testing data about how quickly Claude Opus 4.5 learned.
Cool.
It exhibits this unprecedented self-refinement. It achieves peak performance on a task much faster than its competitors, often needing only 4 iterations to perfect a complex task, where rivals might need 10 or more.
So it's just faster at identifying and correcting its own mistakes. It gets up to speed on a new problem more quickly.
And crucially, Opus 4.5 retains a decisive edge in safe and verified terminal usage. This is what really appeals to security-conscious sectors like finance or defense. Our sources noted it achieved the highest reported score on the industry benchmark, Terminal Bench 2.0.
And in controlled testing, it could do what now?
In controlled tests, it successfully exploited over 50% of simulated smart contract vulnerabilities.
Wow.
Which really highlights its dual-use capabilities, right? It's powerful for both offensive cybersecurity analysis and for defense. It's sort of the secure, fast learner of the group.
Okay, so if we step back and synthesize this, the comparative analysis of these leading models, DeepSeek GPT-5.1, Claude 4.5, it sounds like the raw, verifiable capability is definitely converging. But the utility profiles, what they're for, are fundamentally diverging based on the market they're targeting.
Absolutely. The research data shows that the top-line performance metrics, like, say, verified code writing benchmarks, are now within a remarkably narrow 1.7% margin of each other. But the strategies are completely different.
Right.
DeepSeek wins on priced performance because of that architectural efficiency, and it's threatening to commoditize the entire reasoning layer. OpenAI wins on persistent, multi-day enterprise workflow management because of compaction. And Anthropic wins on speed of self-refinement and that rigorously verified terminal safety. The war isn't about raw intelligence anymore. It's about how that intelligence is architected, packaged, and deployed for specific goals.
It's just astonishing. DeepSeek competing on price, OpenAI on enterprise commitment. But what's even crazier to me is that while they're all fighting over the abstract realm of code and math, the whole field is starting to build real physical things. We now have to shift from this abstract world of reasoning to how AI is integrating with the physical world. This week really felt like the moment AI moved from generative code to generative matter.
It's a huge transition, and it's confirmed across numerous reports our team analyzed. It's the rapid rise of embodied intelligence. These systems are no longer just brains locked away in a server rack. They're getting eyes, limbs, and a really sophisticated spatial understanding of the world around them.
And the major breakthrough here seems to be Google DeepMind's Simit 2. This is the agent designed to reason and act in virtual 3D worlds. But we've had agents in games before. What makes Simit 2 a breakthrough compared to what came before?
The key was the deep integration of advanced language capabilities, specifically the core reasoning power of Google's Gemini architecture. By integrating that high-level language reasoning, Simit 2 effectively doubled its predecessor's performance.
Doubled it.
It can now articulate its intentions, it can explain its step-by-step reasoning for a complex task, and it can genuinely collaborate with users using natural language instead of just following simple, rigid commands.
So it's not just a virtual puppet anymore, it's more like a virtual colleague.
Exactly. But the real aha moment, according to the sources our research team compiled, is its self-learning loop. This is the part with the biggest implication for the future of robotics. Simit 2 exhibits self-directed learning.
Okay, tell us more about self-directed learning in this context. What does that mean?
So when you place it in new, complex virtual environments like sophisticated open-world video games, our team noted examples from things like Asuka or MindDojo Simit 2 doesn't need humans to program or label every single new skill. It uses its own internal reasoning capacity to generate its own curriculum. It creates AI-generated tasks and reward models for itself. It learns from self-generated experience data, and it's essentially bootstrapping entirely new capabilities without expensive, large-scale human intervention.
So it's generating its own homework, it's grading its own tests, and it's getting smarter without needing a human trainer for every single new skill. That has to be a massive saving in development time and cost.
It is. And this training method, where the AI masters complex navigation, tool use, collaboration, all in these cheap, scalable virtual environments, is explicitly positioned by the developers as the foundational building block for physical robots in the real world.
So you perfect a brain in the sandbox.
Exactly. You perfect the underlying reasoning and physical skill model in the virtual sandbox where mistakes are cheap, and then you transfer those core skills to a physical body, whether that's a factory arm or a drone.
And speaking of physical bodies, we saw massive advances in democratizing manufacturing this week, confirming that transition to generative matter. The MIT breakthrough of a speech-to-reality system that is just astounding.
This is the definitive manifestation of turning language directly into tangible objects. This system, it takes complex spoken prompts, it uses generative AI to instantly produce a detailed 3D design, and then it commands a robotic arm to assemble a physical object using modular parts or 3D printing all within minutes.
That democratizes manufacturing and prototyping instantly. I mean, you can literally speak an object into existence just by describing what it does and what its dimensions are. It completely removes the need for specialized knowledge like CAD software.
And this is so vital for accelerating those design to production cycles. You're moving design out of specialized software and into natural language. Just think about a field mechanic who needs a specific custom tool right now, not in 3 weeks from a supplier, or a small business needing quick custom packaging prototypes. The impact on local supply chains and rapid prototyping it's hard to overstate.
This is where it gets really interesting. We're literally speaking objects into existence. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And beyond just prototyping, our sources highlight the immediate industrial application of this embodied AI in logistics. We saw verified reports of autonomous loading and unloading systems in these massive warehouses that are now handling 1,500 boxes per hour with near-perfect reliability.
1,500 an hour.
It shows that AI is really tackling that high labor-intensive logistics sector with unprecedented efficiency and scale.
And the innovation doesn't stop at the warehouse scale either. It scales all the way down to these miniature systems. We saw some breakthrough designs in bio-inspired systems designed for precision work.
Yes, the aerial microbot that's capable of insect-like agility, that was a real standout. I believe it performed 10 flips in 11 seconds. These little insect-like flyers are really poised for things like search and rescue in rubble or inspecting narrow industrial spaces or agricultural surveys, anywhere a large drone or a human just can't safely go.
And we also saw progress in making robots safer to actually work alongside us.
Oh, absolutely crucial. We saw the introduction of a new control system for soft robots that ensures mathematical safety during human interaction. If a rigid industrial robot bumps into a human, it can cause serious injury. Soft robots are designed to deform and adapt, but controlling that deformation safely is a massive challenge.
So why is that mathematical safety control so important?
Well, if robots are going to collaborate with humans on an assembly line in a hospital, maybe in elder care, the system has to guarantee, mathematically, that the robot will deform and absorb an impact safely, preventing harm. This is a key advance over traditional rigid robotics, and it enables truly collaborative human-robot teams. All this together just confirms AI is moving from a digital assistant to a highly sophisticated self-training physical workforce.
Right. And the demands of this new era, the efficiency from DeepSeq, the persistence from Claude, the embodiment from Simit 2, it all means that there's this furious, often unseen battle being fought at the same time on the hardware and the theoretical front. Which brings us to segment 3, the foundation beneath the code quantum infrastructure and theoretical efficiency. The agents are getting smarter, but the machines they run on have to keep pace.
And the first thing our research team confirmed is just the sheer scale of the hardware commitment that's required to sustain this level of activity. The compute arms race is heating up, not just in innovation, but in raw capital expenditure.
We saw the announcement of that $100 billion infrastructure partnership between NVIDIA and OpenAI. I mean, that is just a staggering figure. What does that much money even buy?
It buys capacity, measured not just in chips, but in power. This partnership aims to deploy massive computing capacity. At least 10 gigawatts of dedicated compute.
10 gigawatts.
To put that into context, that is roughly the power output of several small nuclear plants. It's enough electricity to sustain a major metropolitan area for its daily consumption. And this infrastructure isn't just for training the next generation of models, it's for the constant inference, the 24/7 operation of all these autonomous agents we've been talking about.
And of course, the competition is responding in kind with its own specialized silicon.
Exactly. AWS simultaneously unveiled its first 3nm AI chip, the Trainium 3 Ultra Server. The 3nm refers to the size of the transistors on the chip. You can think of them as these incredibly tiny switches. The smaller the number, the closer you can pack them, which leads to these exponential gains in speed and power efficiency.
And this new chip delivers what, a 4.4x performance increase?
A remarkable 4.4x increase over its predecessor. It's just an indication that the hardware innovation cycle is accelerating right alongside the software.
So the industry is scaling infrastructure massively. But the breakthroughs aren't just about building bigger data centers. They're also about working smarter with the hardware you already have. Which brings us to these major discoveries this week around adaptive efficiency.
This is such a critical point for sustainability. The MIT discovery of adaptive LLM computation is a potential game changer for energy consumption. Our research team confirmed this technique dynamically allocates computational resources based on how difficult the task at hand is.
Okay, explain that dynamic allocation.
Yeah.
We tend to think of an LLM as just running at 100% capacity all the time.
That's often true, and it is deeply inefficient. Adaptive compute is like having a modern sports car with really sophisticated engine management. I mean, why run all 8 cylinders at maximum power, burning maximum fuel just to cruise through city traffic? You don't need the full force of a massive, super-intelligent model to answer, what is the capital of France?
So the system is just wasting a huge amount of compute on easy questions.
Precisely. For simple queries, the adaptive LLM system uses minimal effort, kind of like skimming a document on a low-power setting. But when it's faced with a complex reasoning problem, like a medical diagnosis or a sophisticated code debug or one of those hard Putnam problems, the system automatically detects the complexity and it ramps up its resources, engaging all the computational power it needs.
And the potential outcome is huge. Reduction in energy consumption by up to 50% for standard tasks, without sacrificing any accuracy on the high-stakes, hard ones.
If that can be incorporated across the industry, it solves a significant part of the cost and sustainability problem. It makes the whole ecosystem more responsible. It addresses this inefficiency where LLMs are always configured for the worst-case scenario.
And this technical elegance is also coupled with some architectural polishing we saw at the NeurIPS conference this week. Another key finding from the research team.
Right, the gated attention mechanism.
Which was a best paper winner.
So what specific, subtle, but important problem does that solve in the existing transformer architecture? It solves this mechanical inefficiency known as the attention sink. Imagine you're trying to focus intensely on a complex conversation, but every few seconds, a waiter walks by, and you're mathematically forced to dedicate a tiny fraction of your attention to that waiter, even though they're totally irrelevant to the conversation.
So the model is being forced to pay attention to noise it should be ignoring. Where does that forced attention usually go?
In the standard transformer architecture, the math of the attention mechanism is designed so the attention scores have to sum up to 1. So the mechanism is mathematically forced to assign some attention somewhere, even if the information is just garbage. And this waste attention often just piles up on the very first token of the sequence. That's the attention sink.
And that pollutes the model's memory.
It pollutes its short-term memory, and it makes training unstable, especially for really long sequences.
So how does gated attention fix this noisy problem?
Gated attention introduces a really simple but powerful element, a sigmoid gate. You can think of it as a true ignore button. This gate allows the model to output a true 0 attention score to irrelevant tokens. It lets the model completely ignore noise, which leads to much more stable training, improved scaling for those long context applications, and it prevents its working memory from being polluted. It's a great example of how these subtle theoretical breakthroughs can have massive efficiency impacts.
So we're optimizing software architecture with things like sparse attention and gated attention, and we're optimizing resource allocation with adaptive compute.
Right.
These all feel like classical breakthroughs. But then, beneath all of that, Google delivered the ultimate shattering the silicon ceiling moment with a quantum breakthrough that rewrites the future of computation entirely.
This is the second monumental technical leap of the week. I mean, it easily overshadows even the intense reasoning war we've been talking about. Google unveiled the Willow chip, which many in the research community are calling the Wright brothers moment for quantum computing.
Okay, for those of us catching up, what has been the fundamental physics-based obstacle to useful quantum computing up until now?
It's all about noise, specifically decoherence. Qubits, unlike the stable bits in your computer, are incredibly fragile. They exist in a state of superposition, but any interaction with the environment, a stray photon, a tiny vibration, causes them to decohere, and they collapse into a definite state, which introduces an error.
And historically, adding more qubits just made things worse.
It did. Adding more physical qubits to a system actually increased the total noise, making the entire quantum computer less reliable. You couldn't scale without the noise just overwhelming the signal. It was a race against the physics of instability.
So what did Willow do differently?
The Willow chip is historic because it is the first system to definitively demonstrate exponential error reduction below the threshold. That is the key phrase.
And hitting that threshold, what does that mean in practical terms?
It means that as Google used more of these physical error-prone qubits to construct one single reliable error-corrected logical qubit, the system's overall error rate decreased exponentially. This validates the entire theoretical roadmap toward fault-tolerant quantum computers, systems that are capable of running complex computations indefinitely without crashing because of environmental noise. It proves that the engineering reality of error correction actually works, as the theory predicted.
That is a fundamental scientific validation. And the proof is in the benchmark they ran. The comparison here is absolutely shocking, and this is the point that really drives home the scope of this leap.
It is. Google executed a standard random circuit sampling benchmark on the Willow chip. The chip completed the computation in under 5 minutes.
Under 5 minutes, okay.
Our research team noted that Google scientists estimate that executing the same exact calculation on the fastest classical supercomputers we have today, the best the world offers, would take an estimated 10 septillion years.
10 septillion years. That's 10 with 24 zeros after it. I mean, that's a number so vast, it's almost meaningless. To put that in perspective for you, the universe is only estimated to be about 13.8 billion years old. You could run a classical supercomputer from the Big Bang to the present day, 700 million times over, and you still wouldn't be close to finishing this one calculation.
5 minutes versus 10 septillion years. That really puts the scale of the quantum leap into undeniable perspective, even if you acknowledge that the specific calculation is synthetic and designed to highlight that quantum advantage.
Now, while this is obviously a breakthrough of historic magnitude, it's not going to be powering the next version of ChatGPT tomorrow. So what are the realistic implications for AI in the near to medium term?
That's the right question to ask. While Willow validates the path to truly fault-tolerant quantum systems, its immediate impact is not generalized AI. The long-term implication, however, is profound. We saw hints of these quantum echoes algorithms demonstrated on Willow, which suggests a future where quantum computers serve as specialized, irreplaceable accelerators for certain AI workloads.
Like, which specialized workloads, specifically?
Primarily molecular simulation for drug discovery and advanced materials science. The behavior of molecules is inherently governed by quantum mechanics. A quantum computer acts as a native simulator of nature, which would allow AI models to design new drugs or high-performance materials far faster than any classical system ever could, and long-term, quantum linear algebra could revolutionize neural network training by offering speed-ups in navigating the vast, complex optimization landscapes of these massive AI models.
So it's not generalized AI, but it accelerates the scientific and research components of AI development.
Exactly.
Okay, so to summarize this segment, the sheer demand of the reasoning war is driving innovation in three layers at once. We have massive classical infrastructure, we have sophisticated algorithmic efficiency hacks like adaptive compute, and we have this foundational physics-bending shift toward quantum computation. The future is being built from the ground up.
And those foundational battles are being won, which means capability is soaring at an unprecedented rate. Which, of course, brings us to our final and most critical theme, the critical lag. As capability soars, the real challenge moves from what AI can do to how we safely, equitably, and reliably deploy it at scale.
Let's talk about deployment first, specifically the industrialization of AI agents. Amazon Web Services, AWS, launched the Nova family, which signals a major strategic pivot away from that one general model to rule them all approach to these specialized utility agents. What did AWS Nova bring to the table?
AWS is really focused on industrializing agency, making AI agents reliable, boring, and enterprise-ready. They launched Nova Act, and this is a major conceptual shift because it represents the definitive commoditization of computer use. We've talked about agents acting through APIs, but Nova Act allows an AI agent to interface with legacy software through the graphical user interface, the IUI.
That is a massive leap in utility. It means the agent isn't restricted to modern API-friendly systems. It can navigate, click buttons, and interact with some ancient enterprise software, like a payroll system built in the 1990s that was never designed to be automated. How do they ensure it's reliable on such a messy, complex task?
This goes right back to the Simit 2 concept, but it's applied to enterprise tasks. They train the Nova Act agents in these synthetic environments called web gyms, simulated incredibly complex digital internets and corporate dashboards, where the agents practice booking flights, filling out forms, and navigating convoluted internal systems millions of times. AWS is claiming that task reliability is now consistently over 90%.
90%. That's a huge leap over previous attempts at screen scraping or GUI automation. The economic implication there is monumental. Nova Act turns decades of legacy enterprise applications into an instant API layer just by deploying an AI agent to operate the system. Companies don't need these costly multi-year refactoring projects. They just deploy an agent.
Exactly. And furthermore, AWS introduced Nova Forge, which directly addresses that enterprise desire to own their intelligence and protect their proprietary data. This platform allows organizations to create custom, proprietary models they're calling novellas.
So they're creating their own intelligence, not just renting it. What makes Nova Forge different from standard fine-tuning services?
Uniquely, AWS is providing access to pre-training and mid-training checkpoints. This means companies can inject their proprietary data not just by polishing the surface layer of the model, but at the foundational level. This ensures the model's core expertise aligns perfectly with the company's domain knowledge. And crucially, they use these advanced data blending techniques with general knowledge buffers to prevent what's called catastrophic forgetting.
That term, catastrophic forgetting, is important. Explain that briefly for us.
It's a common problem when you specialize a general model too narrowly. If you train a highly intelligent model only on, say, financial data, it might forget how to perform general reasoning tasks, which effectively cripples its broader utility. Nova Forge mitigates this by blending the custom data with general knowledge buffers, ensuring the model maintains its general intelligence while it's acquiring deep specialization. This really pivots the market from renting intelligence to manufacturing bespoke intelligence.
And the regulatory world is paying close attention to this industrialization. Our research confirmed the significant adoption of agentic AI by the FDA and the Department of Health and Human Services, HHS, across their entire workforces just this week.
And this represents the first major deployment of AI agents at scale within a high-stakes U.S. regulatory agency. The FDA is using these specialized systems to accelerate AI-assisted review processes for drug and device approvals. If these systems can reliably manage complex documentation, it could drastically reduce approval timelines while maintaining rigorous safety standards. It's a huge signal that federal healthcare and regulation are moving rapidly toward an AI-driven future.
But this explosion of capability and adoption brings us to the elephant in the room, the governance gap. Across all the source material our research team analyzed, the finding is unanimously corroborated and stressed. Safety and governance infrastructure are critically lagging capability advances. It's creating a massive systemic risk.
The capabilities are real, the governance is aspirational at best. We've seen corroborating reports indicating that despite multiple major companies predicting AGI within 2 to 5 years, none of them have detailed, credible, published plans for reliably controlling or containing a potentially superintelligent system.
It's concerning.
It is. And furthermore, internal evaluations of agent failures often lack transparency, and companies are failing to reliably prevent misaligned systems from escaping simulated human control.
And compounding this serious tangible security and control risk is a fascinating theoretical problem that was highlighted in a NURI IPS Best paper, the artificial hive mind effect. This speaks less to physical security and more to a cultural risk.
This paper introduced a really sobering quantitative analysis of AI diversity. It details how the very mechanism we designed for safety and alignment reinforcement, learning from human feedback, or RLHF, inadvertently trains models toward a narrow generic preference, essentially a bland cultural conformity.
Right. We think of RLHF as the necessary training to make models helpful and safe, to prevent them from generating harmful content. But what's the unintended long-term consequence of that training?
The paper found pronounced intermodal homogeneity. So despite using different architectures, different training data, and operating under different corporate philosophies, the top models from different companies are all converging on the same bland, generic, safe, and unchallenging answers to open-ended, subjective questions.
So the system is optimizing for inoffensiveness.
Exactly. The current reward models, which are optimized for immediate user safety and helpfulness, inadvertently penalize quirkiness, or diverse viewpoints, or genuinely novel perspectives. They're flattening the creative and intellectual output.
This homogenization effect is basically a technological, cultural echo chamber. We're building the most powerful intelligence ever conceived, but we're training it to be culturally homogenous.
And the authors warned that if the world comes to rely on these homogenized systems for foundational ideation, education, and information synthesis, we risk a serious civilizational mode collapse. A world where diversity of thought and creativity are just flattened by our reliance on generic machine output. The system we optimize for immediate safety might end up sacrificing long-term intellectual diversity, making humanity collectively less resilient to novel problems.
This raises an important question. How do we ensure these systems don't become a cultural echo chamber? We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the artificial hive mind effect and AI safety. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
And we also saw tangible, immediate security failures highlighted this week, which really reinforced the reality of this governance gap. The NIST report flagged security shortcomings in open source models like DeepSeq, including things like unprotected training checkpoints and databases.
Which reinforces that tension, right? Open source drives efficiency and democratization, which is vital for competition, but it also creates these serious supply chain risks if foundational security isn't rigorously enforced from day one. It's a real democratization paradox.
The central tension of the week is just unavoidable. The breakthroughs in agentic efficiency, physical grounding, and quantum computation are accelerating at a breakneck pace, but the fundamental safety, governance, and structural security infrastructure, it's
Yeah.
all falling farther and farther behind.
Okay, let's bring these three major themes together for the learner. Let's synthesize what this week really means for the immediate future.
I think the first major takeaway is the definitive shift toward agentic efficiency. DeepSeek proved that architectural innovation, specifically that sparse attention, can now challenge the compute dominance of proprietary models. It's making frontier intelligence cheaper and faster to run.
And at the same time, things like adaptive compute and gated attention are improving sustainability and stability for all models at the foundational hardware level. The era of pure compute brute force is over.
The second takeaway is that AI is grounded. We are watching intelligence rapidly move out of the purely digital cloud and into the physical world. Simit showed that autonomous, self-directed learning in virtual worlds is the path to robust, self-training robotics.
And speech-to-reality systems are democratizing manufacturing and design. The AI now has eyes, memory, and the ability to act on its own long-horizon reasoning.
And the third and central tension is safety and compliance. Capability is just accelerating faster than governance. AWS is industrializing agents that can reliably operate legacy software for days on end. The FDA is deploying them across its workforce. Yet the AI Safety Index reports and the artificial hive mind research remind us that we lack the fundamental control mechanisms to manage this economy without systemic risk and the erosion of intellectual diversity.
So the next phase of AI development, our sources conclude, requires simultaneous progress on all these fronts: capability, safety, infrastructure, and governance. But if we look at the extraordinary success of DeepSeq V3.2 and its self-verifiable proofs, where AI learns to check its own work rigorously to prove its results are correct without needing a human to validate them, the question for you, the listener, is this. Given the massive bureaucratic governance gap we just discussed, should we really rely on slower human regulation to eventually close the safety gap? Or will the next breakthrough be an AI system that's capable of designing and enforcing its own superior self-correcting safety framework? What if the solution to misaligned AI is, in fact, more smarter, self-correcting AI?
That is the question that really defines the immediate future. The solution might just be internal, not external.
Thank you for joining Tomorrow Unveiled for this deep dive into the source material. We'll see you next time as the future continues to unfold.